Yay!
Yay! All right, now let's talk about orbits and see if we can see some of the evidence of how Newton sort of knew he was right. Because what he was proposing was that it's the same force acting on things at the surface of the Earth, which we already know his universal gravitational law can account for that, right? That it's just basically just the same as mg. But does it affect things in the heavens just as well? And that was a major debate back in the time, is that Newton was proposing this as a universal gravitational law, that it's the same laws that affect things here on the Earth as up in the heavens and really throughout the universe. But what's the evidence that he was right? How did he know that he was probably right? Well, what we said last time was if you go a little ways away from the center of the Earth, then your acceleration due to gravity gets weaker, right? Gravitational force gets weaker. What about the moon? It was pretty well known at that point how far away the moon was. So Newton turned his attention to the moon to see if it behaved the way that he thought it should, right? Could he explain the motion of the moon with his universal gravitational law, is the idea. All right, so at the moon's distance, what would its acceleration due to gravity be? We can calculate that. So at the moon's distance, its sort of g out there, right? Its acceleration is just g times the mass of the thing that it's orbiting, which is the Earth. So it's g times mass of the Earth divided by how far away from the center of the Earth it is. And so that would be, well, mass of the Earth we already know. Let's see, the distance to the moon is like 3.84 times 10 to the 8th meters, and then we're going to square it. And so when you do that, what you find out is that the gravitational acceleration is actually really small. Right here on the surface of the Earth, it's like, almost 10 meters per second squared. Out there, it's like 2.72 times 10 to the minus 3 meters per second squared. It's, 2 to 3 millimeters per second squared, so it's really small. Okay, so it's something like g over 3600, which should make total sense. The moon is 60 times further away than you are from the center of the Earth, so the gravitational force ought to be 60 squared, or 3600 times weaker. So that should make sense. Okay, let's see if we can explain the moon's motion then. All right, now what we know the moon is moving in a circle, right? It's asserted that the moon is orbiting the Earth. So that's centripetal acceleration. So if gravity is the force that's holding the moon in its orbit, then its centripetal acceleration is just v squared over r, right? And what we're usually going to say is, what is its orbital speed? Well, that sounds like a tough thing to know. You don't have the moon doesn't have a speedometer on it, but we can get a sense of it because what is speed? Speed is distance divided by time, right? Way back in the early part of physics, you learned that, distance divided by time. So when the moon goes around in one orbit, it goes all the way around in a certain length of time, and that's called the period of the moon. So all the way around is going to be called the circumference of the moon's orbit. So that would just be, the speed is 2 pi times the radius of its orbit divided by the period, distance divided by time, right? We're going to be using this over and over and over again, so get used to seeing this. So if v is 2 pi over t, now I'm going to plug this in, right there. So that means that the centripetal acceleration that we already calculated is what, 4 pi squared r squared, but there's an r in the denominator, so that's just going to be 4 pi squared r over t squared. Okay, well, Newton knew what the period of the moon was. You just watch the moon for a long time and it'll come back to the same point in the sky about 27 days later, right? So let's compute it. What should the period of the moon be? Because we've already calculated A. So t, the period of the moon should be square root of what? 4 pi squared times the distance that the moon is away from the Earth, 3.84 times 10 to the 8th, and then divided by that AC that we just calculated up here. So if you plug those things in, what you find out is that the period is about 2.36 times 10 to the 6th. Oh, but those are seconds. All of our calculations are in SI units, right? Kilograms and meters and seconds. So convert that to days. And you know how to do that, right? There's 86,400 seconds in a day, so divide that. And then what you get is 27.3 days. So Newton could calculate he could calculate what the period of the moon should be if his gravitational law was right. And it turns out that's the right answer. That's the right period of the moon. So there was good evidence that Newton was right. This gravitational law not only explained how things work on the surface of the Earth, but it explains how things move up in the heavens as well. So it was a fantastic synthesis. It was a triumph of Enlightenment thinking. He also, by the way, had a great, probably still the best explanation for what an orbit actually is. We should talk about that. What actually is an orbit? Suppose you have a planet and then some sort of a mountain on the planet, like not to scale, right? Suppose I put a cannon on the top of the mountain and I fire a cannonball. Boom! The cannonball falls to the surface of the Earth. But then suppose I fire the cannon with a little bit more gunpowder or whatever. So the ball goes a little faster, right? So boom, here goes the ball, and then it's going to fall and hit the Earth a little bit further out. But look what's happening. As the cannonball is traveling further away from the cannon, it's falling towards the Earth. But look what the Earth's surface is doing. The Earth's surface is falling away from it at some rate. So all Newton said was, just, in your mind, make a movie of this thing. Keep firing it a little bit faster and a little bit faster. There's going to be some sort of a magic speed where, boom, it comes out of the cannon and it falls towards the Earth, but the Earth's surface falls away from it just as fast, and it ends up going all the way around. It falls around the Earth and comes back and hits you in the head. This was his explanation of an orbit. So in an orbit, you are always falling. This, by the way, is why astronauts in the space station and so on are weightless. They're apparently weightless, not because they're out in space or whatever, far away from the Earth. I mean, just look at a scale diagram of the Earth and where they are in relation to the Earth. I mean, they are, I couldn't even draw it on this diagram. The space station and when the shuttle used to orbit, right? They're just right outside of the atmosphere. Certainly not far enough away. They're inside of the moon's orbits, for heaven's sake. So certainly within the gravitational pull of the Earth. But the point is, they're weightless not because they're outside of any gravitational field. It's because they're falling. They're always falling around the Earth. They're going at a magic speed sideways where the Earth's surface is falling away from them. Let's see what that is. What is that magic speed? We should be able to calculate it. So going back to what we did with circular motion, we just say that the sum of the forces acting on something is equal to the mass times how the thing accelerates, and that's going to be in a circle, right? Centripetal acceleration. The only force acting is going to be gravity. So I'm going to have G times the mass of the Earth times the mass of the satellite divided by the distance away, r squared, of the satellite from the center of the Earth. I'll keep emphasizing the center. Distance between centers is r. And then over here, we have our expression mv squared over r that we've had before. So we can solve for that v. What is that orbital speed going to be? Notice that the mass of the satellite doesn't make any difference, which is good, right? All the astronauts fall at the same rate that the space shuttle falls, which is good because then they float inside the space shuttle. If they're falling at different rates, then they would slam into the side of the space shuttle or something. Okay, so solve for v. So that means that our v orbital speed, if I just solve for v, what I get is square root of g m over r. There we go. That's how you figure out an orbital speed, how fast you have to orbit. That's for circular orbits. That's how fast you have to orbit something. For a low orbit satellite, I mean, basically forget about the atmosphere for a second. So if r is RE, if you're orbiting just outside the surface of the Earth, if you plug those numbers in, the orbital speed is something like 8,000 meters per second, 8 kilometers per second. Pretty fast. That's where all the rocket fuel goes, right? It's not to lift something up to some height above the Earth's surface. That's not actually that hard. The trouble is you need a lot of fuel because you need to accelerate something so that it goes sideways fast enough so that it doesn't hit the ground, right? It's got to go sideways at 8,000 meters per second. What is that? Meters to miles an hour. What do? You double it and add 10%. So it's 17, almost 18,000 miles an hour. So that's where the majority of your energy goes, is to accelerate something to go that fast so it can orbit. How about the Earth around the sun? How fast are we going? It doesn't feel like we're going very fast, right? It feels like everything is standing still, especially to the ancients. But for the velocity of the Earth around the sun, what you would do is, it's always big G. That's always the universal gravitational constant. And it's the mass of the thing that you're orbiting. So it would be the mass of the sun divided by our distance from the sun. Our distance from the sun. So that's going to be 6.67 times 10 to the minus 11. Mass of the sun is 2 times 10 to the 30. Our distance from the sun is 1.5 times 10 to the minus 11. Oops, I don't have to square that, do I? Just GM over R. And when you put all those things in, what you get is about 30,000 meters per second. That's really fast. 30 kilometers per second. What the heck is that? That's going to be 66,000 miles an hour is how fast we're going around the sun, because we have to get all the way around the sun in 1 year. So that's how fast we have to go to get all the way around, right? Okay, so that's how you calculate orbital speeds.